I'm Luke, and this is Maddie, my co-host, and I'm going to be talking about Bayesian inference in generative models. I think I might have erred on the side of too many slides and not enough practice, so I might cut stuff out if I'm running slow. So here's what this presentation is going to look like. I'm going to spend 5 minutes introducing what I mean by Bayesian inference in generative models. And I'll spend a little bit of time talking about exact inference, when you can actually do exact inference. Then I'll start talking about the two kind of broad ways that people do approximate inference, which is Monte Carlo methods and variational Bayes. And then towards the end, I'll quickly brush on some probabilistic programming languages, less than I'd hoped. And then for the second half, we've got some exercises. Got an hour worth of choose your own adventure, implement one of these things. So, I'll get going. So what's a generative model? So a generative model is just any distribution over observations. At least that's what I mean by it. So, linguists might like to build a distribution over sentences by constructing like a probabilistic context-free grammar. Or meteorologists might like to build a distribution that predicts where it's going to rain or what the temperature is. So these are like the latest beautiful samples from a GAN trained on faces. This is the generative model of faces. So, of course, it's perfectly possible to describe generative models for all of these kinds of things without using any kind of hidden variables. People always train RNNs or something on language, train like an RNN language model, or train a pixel CNN image model of faces that generates faces pixel by pixel without any hidden state. But that's not what we're going to be talking about. I'm going to be talking about kind of generative model that's basically causal generative models that try to describe observations through some kind of hidden state, some causal explanation. So in this case, you might think the face is explained by some latent variables that, there's a male face, it's facing to the right, there's short hair, he has short hair, there's a shadow on him. And so if you have a prior distribution over all of those latent variables, and we have some likelihood function that tells us what's the probability of seeing this image given all of these latent variables, then we can use Bayes' rule. And Bayes' rule tells us how to go backwards, how to go from the image and try and infer, what's our posterior distribution of latent variables? Was it a shadow? Was it a moustache? So Bayes' rule just says that the posterior is proportional to the joint distribution. Of course, the maths of Bayes' rule is super simple, and actually doing this thing computationally is really hard. So that's what I'm going to be talking about today. How do you do this thing computationally? So to talk about the kinds of models, to describe the kinds of models we'll be talking about, there's this language of graphical models, and it's a way of drawing the kind of independence structure between latent variables and between observations. So this is the very, very simple causal model here. There's one latent variable, there's a Gaussian, normal, mean 0, standard deviation 1, and then there's one observation that's drawn from another normal distribution centered on that z, that latent variable z. And so in the language of graphical models, often I'll color some latent variable if it's observed. That means I know the value of x. And so once it's observed, Bayes' rule means going from the observations up to the conditional distribution on z, the posterior. Often we'll have lots of latent variables that you kind of want to group together because they all have the same distribution or the same conditional distribution. So in this case, you might have a bunch of different observations, but they're all drawn from the same Gaussian distribution. And so we'll write it like this. We'll put a little box around it and we'll say, hey, there are n equals 3 x variables, and all of them are drawn from the same likelihood p of x given z. So graphical models are a great way to express not arbitrary but pretty rich conditional dependence structure between a bunch of random variables. The reason I say not all, they can't express everything, is because what they can't express is uncertainty over the number of latent variables there are. That's what probabilistic programs are. Probabilistic programs are a kind of generalization of graphical models where you can say we don't just need to infer the values of the latent variables, we also need to infer what the actual structure is. Say I was like rolling a dice or something, and every time I got 6, I got to roll again, and I want the distribution over the sequence of rolls. And so there, I'm introducing a new latent variable every time I roll. And so you need a probabilistic program for that. So how to do inference in something like this? Here's the simple model I was saying earlier. A single latent variable and a single observation conditional on that latent variable. Exact inference, even in this simple model, you can hardly ever do it. In fact, for most distributions you could write out here, it's not just that it's hard to work out the maths, it's that the posterior distribution just isn't analytically soluble. There's no closed form solution for it. And so there are a couple of situations when you actually can do exact inference. One will be if your latent variable z is some discrete variable from some finite set. And then you can just, if it's small enough, you can just enumerate over all of the possible z's and weight them by the joint. If you have a continuous latent variable, it's much, much harder, and you can very rarely do exact inference. The only time you can really do this is if you put a very special kind of prior over z. So some distributions, like the normal distribution is parameterized by a mean and a standard deviation. And there's a very particular class of priors that I can put over those parameters that will mean that in the posterior I'll actually be able to do exact inference. So for a normal distribution, that particular class is to say that the prior over mu is also normal. If I say the prior over mu is also normal, then the posterior becomes normal. And that's no coincidence. In these conjugate prior models, the posterior is always of the same family as the prior. And so there's a whole class of these conjugate prior models. If I have a normal distribution and I don't know the variance in advance and I want to infer the variance, then if I want to be able to do exact inference, the only way I'm going to be able to do that is if I stick this kind of prior over the variance, which is a inverse gamma prior, which people only ever use to do this, really. Or if I have a Bernoulli observation model and I want to know what's the, like a coin flip, and I want to have some prior over the weight of a coin, then I've got to stick a beta prior over that if I want to be able to do exact inference, posterior inference. So there's a super convenient list on Wikipedia of all the different conjugate priors. But for most models I'm going to be interested in, they don't just look like this one latent variable, one observation. And there are some ways that you can still do exact inference even if you have more structured models with longer chains of latent variables. Here we have a chain of z's and a chain of observations. And there's a neat trick that you can do called belief propagation, which says that if all of my latent variables, they form like a chain, or most generally if they form a tree, if there are no cycles between the latent variables, you can't walk through the z's and follow the conditional dependence and come back at the same z you started with, then you can do this belief propagation algorithm. And what that means is you start with building a kind of posterior over z, and you kind of grow it out this way, propagate all the information up to the end of the tree, and then you propagate the information back. And it's just a dynamic programming algorithm that lets you very cleverly enumerate over all of the possible z's without taking exponential time. And so for some models, if your z's are discrete here, or like in an HMM, or if your z's are all, say, Gaussian and you have conjugate priors, then everything's going to work out, and you can do belief propagation, and you can do exact inference in this, exact marginal inference in this whole model. And there are tricks. There's a neat trick called the junction tree algorithm for if your graph is not quite a tree. There are like some cycles, but they're just little cycles, and you just need to like compress them together, and everything is almost a tree. You can kind of twist it to do what you want. But for the most part, you're not going to be able to do exact inference. Actually, for the most part, all of these exact inference methods that I mentioned here, they only really ever play a part as playing a role embedded in some kind of larger approximate inference algorithm. If you build some larger complex model, it's very unlikely that you're going to be able to do exact inference in it, but it is quite likely that there are little pieces of it that you can do exact inference in, and that's going to help you build an approximate posterior. And so that's what I'm going to talk about for most of this talk. Approximate inference. And there are basically two historical strands of these approximate inference methods. There's Monte Carlo methods, which basically start from the assumption that you want to represent your posterior distribution as a collection of samples. And then there's variational inference, which starts from the other assumption that you really want to represent the posterior distribution as a distribution, as some parametric distribution, say like a normal distribution with a mean and a variance. And so these are the two main strands of approximate inference algorithms that I'll be talking about. Another theme that I'll be running through this talk is that actually it turns out that a lot of these algorithms can be made much better in modern days by using neural networks. Sticking in a neural network somewhere as a little proposal function or as a little bottom-up pattern recognition function. And so I'll be talking about ways in which amortized inference can improve these methods. Another theme running through this talk is that all of these methods much more often come from physicists than from statisticians. So Monte Carlo methods, this is, gosh, I don't know how to pronounce his name. I'm going to go Stanislaw Ulam. Does anyone speak Polish and can correct me? Stanislav. Oh, thank you. Stanislav. This is Stanislav Ulam. He's the founder of Monte Carlo methods. The story behind this is that he really loved to gamble, and he would visit this casino, the Casino Monte Carlo, and he was wondering one day about playing solitaire. If you like deal a random deck, shuffle a random deck, and you start playing solitaire by some deterministic rules, what's the chance that you win the game? And he spent a long time trying to work it out analytically, and then eventually he kind of gave up and he thought, you know what, I can just sample a bunch of random decks and play this thing through and then estimate what the probability is that I'll win based on all of these samples. And so he went over to von Neumann, and von Neumann thought it was a great idea. And then they went to work on the Manhattan Project. And so that's the idea behind Monte Carlo inference, is that we want to take a bunch of samples from some distribution, not necessarily our posterior distribution, and want to find a way to use those samples and kind of transform them or re-weight them or something in order to get samples from our posterior distribution. So a really simple version of this is something like likelihood weighting. The model I'm describing here, we've got some agent. He starts over here, and he walks this way, and he has some goal, and we don't know his goal. Maybe we have a uniform prior over the whole space of where his goals could be. But we do have a good model of how he would walk towards his goal. It's like a pathfinding algorithm. So we have some probabilistic model given his starting point and his goal of how he's going to walk. And so one thing that we can do is we can sample a bunch of points from the prior, and then for each point we can look at the probability that he would take this path to that point, and we can just re-weight the points and say, these are the points that had the highest probability that he's going to walk that way, the highest likelihood. And if we re-weight them in the right way, we re-weight them by the likelihood, then that gives us samples from our posterior. It's very inefficient to sample all of your points from the, hey.
So what's the likelihood in this case?
The likelihood. So the likelihood, well, I'm brushing over it because I haven't written out the model. I suppose we would, given some stochastic pathfinding model, the likelihood is the probability that the agent would walk in exactly this path, given that he has that end goal in mind. I would imagine something like you take a deterministic pathfinding model and then you add a bunch of noise. But sampling from the prior like this is going to be quite inefficient, because actually to begin with we probably have quite a good guess of where the agent's going. He's going somewhere over here on the right. And so important sampling is this idea that, okay, so we sample from some guide distribution Q, and then Q is this green distribution here. We sample a bunch of points from that guide distribution, and then we can reweight them by this importance weight, which is the joint distribution divided by Q. And if you do that, everything works out perfectly. And the question is, how do you get this distribution Q? And this is the great place that neural networks have come in. Neural networks have come in as a way to say, okay, take this image or this video of an agent that's walking down here and run it through a convolutional network or something, and get that network to output something like a Gaussian distribution. And that Gaussian distribution, you don't expect it to be exactly right for the posterior, but you do expect that it's going to be a good guess. And then you can use importance sampling to kind of clean up the samples with the model in the loop. And so this is what Marco does. Marco Cusimano-Tauner. He's a graduate student here in Vikash's lab, and he has a great model where he does just this. He has a pathfinding algorithm on a drone, saying a drone is trying to explore this area and get to some end goal, and we don't know where it is, but we observe its path. Where do you think it's going to land up? And he runs it through a neural network, and he does importance sampling, and it works great for him. So this is importance sampling. It works really well if you have a good guide distribution, but your guide distribution has to put a ton of mass where the true posterior is, and particularly in like really high dimensions, that just doesn't ever work. And so that really motivates methods that can kind of be a bit more adaptive. And so the idea of these Markov chain Monte Carlo methods is that rather than sampling a bunch of points independently from the start, you kind of build up a chain of samples where you allow each one to be conditioned on the previous one. And what that means is you can kind of integrate feedback from your actual model in the loop. And you can hopefully build up a Markov chain such that over time your samples will end up being distributed according to the posterior distribution. So I'll show you what I mean here. Here's an example. This is a mixture of Gaussians model. So the model here is that I have a bunch of points and they're drawn from some clusters, and I don't know what the cluster means are, and I don't know which point was drawn from which cluster. And I want to learn what the assignments of points to clusters are, and I want to learn where the clusters are. And so Z is some categorical distribution that tells me for each point which cluster is it in. And mu is some normal distribution that tells me for each cluster what does its mean. And so this puts us in a kind of position where, you know, we can't really solve this thing directly. We can't do posterior inference properly. But if we knew what the Z's were, if we knew the assignments, it'd be really easy to work out the mu's. We just put a ring around them. And if we knew the means of the clusters, it'd be really easy to assign the points, because you just put them near the nearest cluster. And so this kind of sets up this, you don't have a handle on the joint, but you have a handle on these kind of conditional distributions. So this is what Gibbs sampling is for. Gibbs sampling is when you have a joint distribution that you'd like to sample from over these two variables, in this case Z and mu, and you know the conditional distributions even though you don't know the joint. And so this suggests this kind of alternating procedure where you sample the Z's given the mu's, and then the mu's given the Z's, and the Z's given the mu's, and it turns out that when you do this enough, you end up with a sample from your actual joint distribution. You'll notice that we set the problem up with all of the right conjugate priors here. So Z is a categorical distribution, and pi is the conjugate prior for a categorical distribution. And what that means is, so this variable pi is used to represent the proportion of elements in each cluster. Pick a random point and what's the probability that it ends up in this cluster. And the reason that we've set up all of these conjugate priors here, we've given mu a conjugate normal prior because that's the conjugate prior for the mean of the normal likelihood. That means that we can kind of collapse the whole thing. And in this case, we don't actually need to sample pi at all. Because we use conjugate priors, we can always integrate out pi. We can sample mu given z and z given mu, and we never need to look at pi at all. And so that's an example of using these kind of exact inference in the middle of an approximate inference algorithm. But in most cases, you're not going to have anything like this. You're not really going to know your conditional distributions perfectly either. And so what do we do in this situation? And what people like to do is something a lot similar to importance sampling, which is that you sample from some other distribution. It's not really the conditional distribution, but hopefully it's something like it. Hopefully it's a bit close to it or something. And then you kind of reweight them, or you accept or reject them, these proposals. And so this is the idea of Metropolis Hastings sampling. And I'll show you a video of what it looks like. Can I do this? Maybe it's here. Oh yes, here we go. I love this. Okay. So we are this little point. Let me slow it down. We are this little point, and we're trying to sample from this global distribution. This is the density. It's like a big Gaussian distribution. And at every time step, we're going to make a proposal that says, should go over here, should go over here. And what it's showing is green if the proposal is accepted, and red if the proposal is not accepted. If the proposal is not accepted, then you just stay where you are. If the proposal is accepted, you jump there. And the way that the proposals get accepted and rejected is by this math. It just turns out that when you do this maths, this is the kind of generalized version of that importance sampling that we saw earlier. It turns out that when you accept and reject these proposals, these jumps, by exactly this proportion, then if you run this thing for long enough, you end up with samples from the true posterior, which is miraculous. But it's kind of terrible as well. It doesn't really work very well, and most problems that you'd actually be interested in, unfortunately. There are a ton of other ideas to make MCMC work better, and these really do work quite well. So this classic data-driven proposals thing, a lot of people have been training neural networks to help do MCMC. So one thing that you can do is you can train a bottom-up recognition model, and you can use a mixture distribution of proposals, a mixture that says, say with 50% probability, you take one of these local Gaussian proposals or something, and with 50% probability, you sample from this neural network global distribution. So Tejas, those of you who know him from our department, he did something like this in Picture, where he wants to infer the 3D geometry of someone's face, and he has a neural network that gives you a good global guess at the 3D geometry of their face. And then he does MCMC, moving around that space, and renders. Maybe I can miss these two things, but one thing I do want to tell you about is Hamiltonian Monte Carlo. A real limitation of lots of these methods is they really don't work very well in high-dimensional spaces at all. They're really bad at exploring high-dimensional spaces, and Hamiltonian Monte Carlo is one great way out under the assumption that you have differentiability. Say you have some big model and all of your latent variables are differentiable. If you can actually differentiate the log joint with respect to your latent variables, then Hamiltonian Monte Carlo is an MCMC algorithm, and what it's basically like is rolling a ball around the landscape. Imagine this is like a frictionless landscape. and you roll a ball and it climbs and it falls. And when it's at the hills, up here, it's really slow because it's lost all of its kinetic energy because it used it climbing up. And when it's at the troughs, it's really, really fast because it's just come down a hill. And what that means is it spends a lot more time at the parts of the distribution that are really high than the parts of the distribution that's really low. Unsurprisingly, this was one of the many ideas that came from statistical thermodynamics alongside Monte Carlo methods and variational methods. And so I can show you what that looks like and how much better it looks like than MCMC, than Mitropoulos-Hastings. So each step here is one iteration of rolling the ball for something like 100 time steps or something. Roll the ball along the landscape and then stop it and then pick a new direction and roll it along the landscape again. And it works really well. It's like really effective at exploring the contours of this landscape. And so if you have gradient information, the take-home message is this thing is wicked. Hamiltonian Monte Carlo. Okay, right, half an hour. I'll slow down a bit. So, to summarize a bunch of MCMC methods. They're really general. You can apply, oh, you can't see what I'm looking at. So to summarize, MCMC methods, they're really general. There are a ton of different specialized methods for working with high dimensionality or with continuous differentiable variables, discrete variables like probabilistic programs, structural uncertainty. But where they have a lot of difficulty is a couple of places. One, they can make it really difficult to jump between modes of a distribution. It's very easy to get stuck in a distribution like this, in a mode like this, and you're really unlikely to come all the way down here and make this trek up to this mode of the distribution. Sometimes it's hard to find a mode at all because you just start in some flat part of the space, and unless there's some kind of gradient or something that's pushing you in the right direction, there's no reason to expect you're going to be pushed towards a mode of the distribution. And lastly, it's hard to know if the thing has converged at all. There's no marker that when it's time to stop and take your posterior and say this is it. And actually, this is a real problem in practice.
So what do people normally do?
Sorry?
What do you do then?
What do people do? Well, okay, so there are some people have got better at doing this recently. Marco Cusimano-Tauner, whose work I pointed towards a moment ago, he's the guy who did this this paper. If you look him up, he has a great paper from a year ago in which he tries to estimate the convergence of MTMC sampling algorithms like this. But it's still a hard problem. And I think that since I don't have as much time, I'm going to skip over this thing. Isn't it pretty though? Okay. And I'll start talking about variational inference. So, variational inference. This is Euler and this is Lagrange, and they are the kind of founders of the calculus of variations. And the calculus of variations is what you use if you want to solve an equation where the thing that you want to solve for is a function. Solve for f. And so variational inference is about this kind of thing. It's about, we have some function class. In this case, it's a distribution, like a normal distribution. And we want to solve for what's the normal distribution that is closest to the true posterior. So what I'm showing you here is a true posterior in grey, which I'll call P, and the variational inference problem is to find the distribution that matches P as well as it can by this measure. And this is what's called the KL divergence. And the KL divergence is a measure of the distance between two distributions. It's always positive, and it's 0 whenever the distributions are exactly equal. And so what that means is that we've got our ground truth posterior, and we want to minimize the KL divergence between the posterior and our variational distribution, Q. So unfortunately, we don't usually know the actual posterior. We can't evaluate the actual posterior, but what we can evaluate is this thing, the joint probability of our observations and our latent variables. And so in practice, in variational methods, people usually optimize this thing instead. This is called the elbow, or evidence lower bound. And it's called that because it's a lower bound on the marginal likelihood of your data, this kind of like model evidence idea. The lower bound on the probability of your data X marginalizing over all of the Z's. And so we want to maximize this model evidence, which corresponds to minimizing the KL divergence between the posterior distribution and our variational distribution. And the question is, how do we choose a variational distribution? Like, what family do we want it to come from? And how are we going to optimize it? And so historically, people have done this a couple of different ways. There's a kind of old school classical variational inference that I guess started around the 90s and went on into the 2000s and is still alive and well. Sorry, go away Java, please. And that means that in classical variational inference, we're going to try and find some variational family that has really particular properties that means that the maths is going to work out, basically. We're going to use conjugate priors everywhere we can and things like that to make sure that we can optimize this variational distribution analytically, and we can derive the right update equations for it. Very contrasting to that, more recently has arisen this kind of stochastic gradient variational Bayes. And the idea here is that you can kind of parameterize some more arbitrary distribution, some more arbitrary continuous distribution, and rather than deriving analytical updates to it, you just kind of do gradient descent, and you kind of take gradient steps to push this distribution closer to the posterior. So I'll talk about classical variational inference first. So we're going to start by picking a conjugate prior distribution over P, and we're going to choose a posterior distribution from the same model family. So back to this kind of mixture of Gaussians example, I've said every Gaussian not only has a mean but has a covariance matrix now, and we've got this pi, which is with the cluster proportions, and so we'd like to infer jointly all the z's and the pi and the mu's and the sigmas. And the thing is that in the posterior of this distribution, this is a very reasonable sample from the posterior, you might expect. And this also is a very reasonable sample from the posterior. And what's really not a reasonable sample is this. There's this kind of dependence that like one of these two clusters has to explain this point, but they can't both explain it, or they don't both need to explain it, and they can't neither of them explain it. And so despite the fact that all of the mu's and the sigmas are independent in the prior distribution, once we've conditioned on the data, they're no longer actually independent. In the posterior distribution, there's these kind of correlations between these latent variables. And unfortunately, that makes it really messy. So what people do in classical variational inference a lot of the time is they use this thing called a mean field approximation. And what that means is that we're going to assume that in our approximate posterior, none of the variables are correlated. We're going to build an approximate posterior distribution over mu and pi and sigma and z, that just factorizes as a product of these independent distributions. And so it's kind of like, it's kind of like saying that you find the closest match to the posterior without allowing any correlations. If that's P is our true posterior, then we might find something like this kind of orthogonal Gaussian distribution, say, where we forced Z1 and Z2 to be independent in the posterior. And so when we set the problem up like this, we build a posterior that say factorizes as the posterior over Z and mu has to be a product of these two independent distributions. We're left with something that looks a lot like what we had in the Gibbs sampling scenario. So kind of like, if we knew what QZ was, we could solve analytically to find the best Q of mu. And if we knew what Q of mu was, we could solve analytically to find the best Q of Z. And so it suggests another kind of alternating update algorithm. We alternate updates to these two independent factors in the posterior. And that's the way that kind of classical variational inference has typically worked. You move back and forth between minimizing this elbow with respect to one of the distributions and fixing the other, and doing it the other way around. But you might ask, can't we just do all this with gradient descent? And it turned out in 2014 that you kind of can just do all this with gradient descent, at least with some other assumptions. You need to make sure that, suppose you want a variational posterior Q that you need to make sure it's continuous, obviously. You can't have gradients of discrete random variables. Or when we try, it doesn't tend to work very well. And they need to be reparameterizable, which is a kind of technical thing that gets introduced in this paper here, but a lot of interesting distributions are, normal distributions are. And so when you do this, you can throw away all of these conjugate priors, and you can throw away this kind of mean field requirement that your approximate posterior has to factorize these really restrictive independence assumptions. But you can just kind of build a fairly arbitrary continuous differentiable posterior and just run gradient descent on it. And that's the idea. And so here's an example of what that might look like in Torch. Here's some Torch code that I wrote a few hours ago. And here's a model that I might want to do inference in. So I have a prior distribution over Z, and that's a gamma. And I have some weird likelihood function that I wrote out. That is kind of Z minus X to the 4, an exponent of Z minus X to the 4. At least it's an unnormalized likelihood. And so there's certainly no conjugate distribution that I know of. There's no conjugate prior to this likelihood. And even if there was, I'm not using it. And so I'm going to write out a variational distribution Q that is also a gamma distribution. I'm going to say my posterior is still something like a gamma distribution. But I can't solve for it analytically because it's not conjugate. But what I can do is I can say, hey, theta are the parameters of Q. That's this A and B parameters. And I'm going to say, I would like to optimize Q towards this elbow. The elbow is just the log joint minus the log probability under Q. Or looked at another way, it's the log phi minus log probability under Q, which is a KL divergence, and then this is a likelihood function. And so it's super simple to just write out this elbow in Torch and then say, hey, I would like to take gradient steps on this. And the way that you take gradient steps is that you sample from Q and use that to estimate the elbow, which is what's happening here. Where? Here. I take a sample from Q and I use that to estimate the elbow. And that's going to give me an unbiased approximation of the gradient towards minimizing the KL divergence. So there's been a ton of work on this kind of stochastic gradient variational Bayes recently. I won't mention most of it. One thing that I think deserves mentioning is this idea of normalizing flows. That's a way of fitting very, very rich expressive posterior distributions to get as far away as you can from this kind of mean field assumption. And the way that it works is you might describe a posterior distribution by saying, well, we'll start with a simple distribution, like an isotropic Gaussian distribution, and we'll run it through a sequence of transformations, a sequence of invertible transformations, bijections, and they're going to stretch it and twist it around. And you can start with a simple unimodal distribution and end up with some huge stretched out multimodal distribution and fit that to your variational posterior. And so that really gets over one of these huge limitations that's been problematic for a lot of variational methods historically. Another thing that has worked tremendously well for people doing variational inference recently is throwing a neural network on it. So you can parameterize your variational posterior with a neural network. If you have some model that says you have a bunch of x's and for each x you have some latent variable to explain that x, then you might think that the z's are actually quite predictable from the x's. So predictable that instead of describing a separate variational distribution for each of these z's, you might just describe a function that goes from x to a distribution over z, gives you the parameters of a Gaussian distribution or something. And so that's what people do. That's what variational autoencoders are doing. They're describing a variational posterior on latent variables using a neural network, and that's how it parameterizes it. And what this means is that once you've done inference, you not only have solved the posterior inference for each of the x's that you had in your training data, but you've also got a bottom-up recognition network that's going to generalize to inference on new data. So variational methods, they're super fast. They're a lot faster than MCMC. They give you a readout of this thing, the model evidence, which is a lower bound on the marginal likelihood of your data. And you can fit really arbitrary distributions nowadays, or not quite arbitrary, but really expressive posterior distributions, not like you used to be able to. But unlike, say, Metropolis Hastings, they do still place some pretty severe restrictions on the model. So for these kind of classical variational inference methods, you're really restricted. People would always choose these kind of conjugate via mean field models because that's what you could derive the updates for. For these like stochastic gradient variational Bayes methods, you're really restricted that everything has to be differentiable. If you want to build a model and it has, say, a non-differentiable renderer in it or something, that's going to make it much harder. And we're still working out how to get these methods to work for discrete latent variables or for non-differentiable generative models. And the last thing I'll say about this is that unlike MCMC, it's not like you can just keep running this thing for longer and longer and eventually you get to the right answer. At some point it converges, and when it converges you don't have the true posterior, you just have an approximation to it. The last thing I want to talk about very briefly is probabilistic programming languages. Talk about a few probabilistic programming languages. And I think they've kind of come through from a few families. So Stan is by far the oldest thing that I'm showing here. Stan is named after Stanislav. And Stan is a kind of older, highly optimized probabilistic programming language that's going to give you really good abstractions for doing very fast inference in like fixed graphical model structures. And Edward, I would say, is a kind of something like a successor to Stan. Stan for the new millennium with, deep generative models, neural network generative models, and like 40 times faster GPU accelerated Hamiltonian Monte Carlo, but still fundamentally restricted to graphical model structures, not these kind of arbitrarily expressive dynamic probabilistic programs that can reason about an unknown number of latent variables. So coming in at the other side is web people. Web people came from Noah Goodman and Andreas Stollmuller as an offshoot of Church, which was developed when he was here. And web people is going to let you reason about all of these kind of arbitrary, in the limit, kind of universal, they say, probabilistic programs, which means that you can express any probability distribution, including probability distributions over an unknown number of latent variables. But web people has been superseded, it seems, by Pyro. And I was hoping to have a bit of a tutorial on Pyro in this class. And then it transpired that a bunch of us are getting together to talk about Pyro and learn how to use it on Thursday. And so I want to advertise this thing. If anyone wants to learn about Pyro, Pyro is web people for the new millennium. Pyro is web people plus neural networks, basically. Web people plus really good stochastic gradient variational inference, deep generative models. It has MCMC and all that stuff, but it's really pushed towards variational inference. And so it would be great if anyone would come and read Pyro and implement Pyro things with us on Thursday. And the last thing I want to talk about is Gen, just to advertise Marco's wonderful probabilistic programming languages that is almost ready, I hear. The angle that Gen's coming at is kind of different to all of these things. The angle that Gen's coming at is that for like a ton of these algorithms that I was describing earlier, kind of like Gibbs sampling or MCMC or variational methods, all of these, amortized inference, all of these things, there's some sense in which a lot of these things are like really very composable. You can like mix, with MCMC methods you can choose, I'm going to take these variables, they're differentiable, so I'm going to run HMC on them. These variables, I can't really do anything with them, I'm just going to run Metropolis Hastings. These ones I'll run some Gibbs sampling on, these ones I'll collapse out. The idea of Gen is to let you really express all of those kinds of things and more, express your own inference algorithms, to like program in fairly composable inference algorithms. And so with that, I'd like to direct you to Marco. Okay, what time is it? Am I on time? Yes, I'm on time. Okay, good. All right, cool. So that's the end of me talking bit. That was quite a lot of things I just said. We made some exercises. Me and Maddie made some exercises. And it's a kind of choose your own adventure of, do you want to implement one of these things? If you like Metropolis Hastings, you might want to learn how to implement a Metropolis Hastings sampler. We have built a generative model, and it's Bayesian linear regression. So we have a bunch of data, and that data is described by some polynomial, and we don't know the polynomial. We don't know any of the terms in the polynomial, but we want to stick a normal distribution over those terms, and we want to infer what is the latent polynomial that describes this data. You can implement a Metropolis Hastings algorithm for this data on our little IPython notebook. Or if you choose to do a ton of maths, if you'd like to do a ton of maths, you can derive the optimal old school variational inference updates for this model, try and analytically optimize the elbow and see what that feels like. And it feels like a messy last night and lots of scrap paper, but we did it, and we have the right answers to show you. Or if you want to do stochastic gradient variational Bayes, then you can do that too. We have set it up so that you can describe a variational posterior and one gradient descent and learn this posterior distribution over functions without having to do any maths at all. With that, you're welcome to go. And anyone who wants to stay, I'll point you to the exercises.